A tray of dough sitting on a counter. Someone stands over it and throws in the chocolate chips at random. Not carefully, and not one per cookie. They just fall wherever they fall. Then the whole slab gets cut into 100 equal cookies, 10 across, 10 down. Here is what you want, not most of them. Every single one of those 100 cookies has to come out with at least one chip in it. One bare cookie, and the batch has failed. And you do not need that to work every time. 9 batches out of 10 is good enough. So the question is simple to say. How many chips do you throw in? Pick a number now, before we start. The number you pick is genuinely the interesting part of this problem.
Almost everyone answers this in about 2 seconds, and almost everyone says a few hundred.
Here is where that comes from. 100 cookies, so throw in 100 chips, and now every cookie has 1 chip on average. On average. But the chips do not line up politely. They land where they land, and with exactly 100 of them, the chance that every cookie gets served is smaller than 1 in 10 to the 40th. That is not a small number. That is a number you will never see happen. So people push their guess up. 200, 300, 500 feels generous. 5 whole chips for every cookie. Throw in 500 chips, and every cookie is served about 51% of the time. Half. You would lose that bet as often as you win it, and we asked for 9 times out of 10.
This problem is not really about cookies. It is one shape out of a family. Something has to reach everywhere, and the question is how much of it you need. Servers and requests, doors and a leaflet through each one, cookies and chips. Learn the shape once, and you stop meeting these one at a time. I have coached hundreds of people through this pipeline, and some of them ended up in the seat they were aiming at, north of 500,000 a year. Shapes are what I taught them. The Quant interview playbook is where the whole set lives. 281 worked exercises, and every solution names the move before it touches any algebra. Link is in the description. Now, back to that 500. Let us stop guessing and count. Start with 1 cookie. Just one. The one in the corner. And forget the other 99 for a moment. A chip falls into the dough. It has 100 cookies it could land in, and it picks one at random, so it misses our corner cookie 99 times out of 100. Throw in a second chip. It also misses 99 times out of 100, and it does not care in the slightest where the first one landed. So the corner cookie comes out bare only if every single chip misses it, which means you multiply 99 over 100 by itself, once for each chip you threw. Let me write n for the number of chips, since we are going to be moving it around. The chance that one named cookie ends up empty is 99 over 100 raised to the power n. And watch how fast that collapses. With 100 chips, a named cookie is still bare more than a third of the time. With 500 chips, it is down to about 7 in 1,000. It keeps falling, and the only question left is how far it has to fall. 1 cookie was never the job. 100 cookies are. And this is the sentence the whole problem turns on. There is not one way for the batch to fail. There are 100 ways, one for each cookie, and any single one of them ruins the batch on its own. So add them up. 100 cookies, each one bare with the chance we just worked out. Multiply that chance by 100, and you have the average number of bare cookies per batch. Now watch what that buys you. If, on average, fewer than 1/10 of a cookie comes out bare in a batch, then batches with a bare cookie in them cannot be happening more than 1/10 of the time. You cannot average 1/10 of a failure while failing more often than that. So push the average number of bare cookies down to 1/10 of 1. 1 bare cookie in every 10 batches. Solve for the number of chips, and you get 600
688. That is a real answer, and it is genuinely safe. It is just not the smallest one, and the reason is a double count. When a batch comes out with 2 bare cookies, adding the 100 chances up charges you for it twice. Once for the first bare cookie, once for the second. So the sum reports slightly more failure than really happens. And 688 is slightly more chips than you need. So take the double count back. Go and count the pairs. 2 named cookies both come out bare when every chip misses both of them. And a chip misses both of them 98 times in 100. There are 4,950 pairs of cookies, so subtract 4,950 of those. Except now the batches with 3 bare cookies have been taken off once too often, so you put the triples back in. Then the quadruples come out again, plus, minus, all the way up to 100. That alternating sum is exact, and the idea behind it has a name people use: inclusion and exclusion. The lovely part is how quickly it stops mattering. Around the number we are chasing, the first piece is about 1/10. The pair correction is about 5/1000ths. Everything after that is too small to see. 2 terms already settle it. Run the whole sum, and the smallest number of chips that serves every cookie 9 batches out of 10 is 683. Not 500, not a few hundred. 683 chips for 100 cookies. And if 9 out of 10 is not good enough for you, 99 out of 100 will cost you 916. Now look at what that number actually is, because it is not the number of chips a batch needs. Throw the chips in one at a time and watch the tray. The moment when the last empty cookie finally gets one is itself random. Some batches finish early. Some drag on. Half of them are done by 497 chips. On average, it takes about 519. Which means the reflex answer was not stupid at all. 500 is roughly where this finishes half the time. It is the typical answer, and the person who says it has good instincts. The question just did not ask for typical. It asked for 9 batches out of 10, and buying that extra safety takes you from about 500 chips to 683. Wanting 99 out of 100 takes you to 916. That is what a long tail costs. The last cookie is stubborn, and every extra 9 you ask for costs more than the one before it. There is a standard estimate for this shape of problem, and here it lands at about 691. Close, and on the high side, which is what estimates of this kind tend to be. And the shape has a name you have met without being told. This is the coupon collector. Cereal boxes with 1 prize inside each, and the last prize is the one that never comes. So what was this question really testing? It handed you an average and dared you to use it. 1 chip per cookie on average. And the average turns out to be the one number in the room that tells you nothing. Because a batch is only as good as its worst cookie, and worst cookies live in the tail. Almost every risk question a desk asks has that same skeleton underneath it. Never what happens on an ordinary day. Always what it takes to be fine on the bad ones, and how steeply the last stretch of certainty is priced. Which is the part nobody drills. 3 ways strong candidates lose this one. They compute the average and stop there. They get the right idea, take the first bound they can prove, and hand over 688 without noticing they overshot. Or they see an alternating sum with 100 terms, panic, and never spot that 2 of those terms settle it. None of that is a knowledge gap. It is the wrong shape of preparation for what is actually being measured. 15 years recruiting in finance, from the side of the table where the decision gets made, is where the Quant interview playbook came from. 411 pages. 4 tracks, because trading and development and hardware and research are not the same interview. 4 mock interviews, with the scoring written down the margin, so you can read what was being noted while the candidate talked. Link is in the description, and I would go and get it before your next batch of applications goes out. 100 cookies, 683 chips,